In this topic, I'll be talking about the abstract syntax tree. And speaking of visiting the source, when we talk about things like visiting the source code of libraries that we like to use, such as matplotlib or such as pandas, we can read through things as .py files. But what if I want to figure out how Python reads things? I can reason about things on my own. How does Python know that when I assign x equals 4, it needs to load the value 4 and store it into a variable named x? Well, we can use something called Python's abstract syntax tree, or the AST module in Python. And you can see here when I run this code cell, I get this really odd representation of what this code actually is. I see it's wrapped in a high-level module. I see that that module has a body that's a list, and I see that that list contains something called a sign, and it has a target, and that target is named x, and what's it doing? It's storing something. Okay, and then what's it storing? Well, it's storing just this constant, and that constant has a value of 4. And so we can reason about this. We can say that Python needs to have the ability to parse the human-written, the human-readable text that we provide it, because it has to, at some point, translate it to something that our computer can understand. And when we look at Python's execution model, we see kind of this dichotomy, or this continuum of static human-readable source code all the way down to machine code. So here on the left, we have our source, and then all the way at the end here, we have machine code, right? If you were to give me machine code, nobody can read that. That's not meant to be read by people. And there are very discrete steps that we do, that Python does for us, actually, in order to get from source code all the way to machine code. And in terms of translating the source into that structure we just saw above, the AST, it does just simple parsing. And so we're going to be discussing this exact, this specific, I should say, process here. But how does it parse? Is this just a bunch of regular expressions? What is going on under the hood? I can tell you that from your everyday perspective, you don't need to really know how Python parses, but what's very interesting is knowing these steps that it does parse. So if I have code here that's kept in a string, in the very exact same way that your code is kept in a file, I can go ahead and I can tell Python to go ahead and parse this code and then print it to my screen, just as we saw above. And we can see here that this is slightly different than just assigning x equals 4. In fact, we're using what's now called a join string, which is a node that represents an f string. And in fact, I can go ahead, I can have it parse a lambda. And you see that we always end up with this tree-like structure that starts with a module, has a body, and then in that body is just more and more branching depending on all the things that we want to do. I can even have invalid Python syntax, right? This return, if I were to try and execute this code, Python would complain, say, return's not inside of a function. A return can only ever appear in a function. But Python will still parse this. And that actually tells us something very interesting, is that Python doesn't necessarily always check our grammar before it moves on to the next step of either trying to create bytecode or run that specific code. It can still very readily parse this even though it's invalid Python syntax. But what can we do with Python's AST? Well, we can do some actually quite fun things. Since, as I mentioned, we're grabbing Python, we're grabbing source code in this intermediate step, right? We're able to manipulate this source code and do whatever we want with it, and we can spit out an AST however we want. And then just by intercepting it there, we can pass that on to be actually run subsequently. And so when we go ahead and play with this metric, we can do, like I said, some very fun things. And so I'll go ahead and I'll print out this tree-like structure. We see it's just an AST module, and if I were to dump this, right, you would see it's a bunch of imports, and it's a function right in the middle of all these imports. What I would like to do is some automated way of sorting these imports. I want the imports to all be at the top, maybe in alphabetical order even, but I think, in my code linters, I love it when all my imports are at the top. I think it's easy to read. It declares what you're going to be using throughout that module. Now, there are some, use case scenarios where an import shouldn't necessarily be at the top, or should be some logic before you try and import something. But we'll forgo that for the much simpler cases. How would I go about moving all of these import statements to the top without actually changing my source code by hand? Well, we can leverage Python's AST. I can actually walk this tree-like structure, and I can do that just by iterating over that .body attribute. And I can print each node. And you see as I print each node, I get import from, I get an import, a function def, and then so on and so forth. Well, what if I wanted to reorganize some things? What if I wanted to make it so that the imports are at the top? I could probably just check if a node is an instance of import or import from, and then just put that in a list, right? Because the body of the module is just a list of nodes. So I can probably reorganize these how I see fit. And let's just go ahead and see that this is working. Should have a list of import nodes. Yep, that seems to be working. And if it's not an import or an import from node, let's append the node to the rest. And just with maybe 6 lines of valid Python code, I have separated all of the import statements from literally everything else. But how can I go about just to recreate this code? Well, I can lean on something like unparse, and I can store it into a new module. So let's go ahead and let's check this out. Make a new tree who has a body who's just the imports for now. And all the unparse does is it will traverse your tree that you're working with, and it'll actually turn each of the nodes back into human readable source code. And I see here there's something called type ignores. Just pass that as an empty list. That should be up here. All right. Type ignores with an S there. And there we go. Those are just my imports. I've completely removed the body. And I can reestablish the order, the human written code, just by using Python's AST module. Now I can go ahead and I can do very fun things, like I can sort the imports before I put them in, and we would need to use a key function here to do that. Go ahead and run that, because there's no, right, these are comparing nodes. So if I had to write a key function like this, let's see, make sure I invert that. All right, and we can reason about these nodes. Let's use a match here. And import right? And now I'm printing each import as it comes in. And we can reason about these types of things, and by grabbing different attributes, I can, from the specific import, for the import from, it's actually quite straightforward. You can just grab the name that's associated, or the module that's associated. Right, and so here you see that I grab matplotlib. And then for this, we'll have to dig just a little bit deeper. It'll actually be the name of the node. So the node.names, get the first element from that. And then from that first element, get the name. We'll partition this out on I believe a dot. And we'll just grab that first element here. Case import from, that should be good, should be good. Yep. Make sure I have my import node here. We can always do this with an if is instance check. So let's go ahead and do that. Right. Node module from. It should be import from, not module from. Yeah, import and import from. But we can use these types of tools to our advantage to do what is really, at its core, some metaprogramming stuff. I can use language, use code that generates other code, and that's really what Python is. Here we go, and you see I have the names there. And we'll just go ahead and return that name. And now I've sorted all my imports and I've put them back exactly as they were. I can attach the body back to this or the rest of the text as well. So let's go ahead and do that just so we have a full-fledged solution here. And there we go. I've completely recreated my source code from my AST, manipulated my abstract syntax tree, so I insert the module imports at the top, and then I have the rest of my code below it. And this is kind of like a very precursor to a tool like isort. Now, can we do that without AST? Absolutely. We can specify some complex grammar, some regular expressions, something of that nature to grab all those import statements on our own. We can make sure we're grabbing our code from the actual original source code. We're not having to lean on this unparse, which actually might change the specific text that we've written, but it's definitely doable without the AST. Then what's the point of the AST? Well, the AST is our link into Python's grammar, Python's parser. We're able to leverage Python's parser, have it parse itself because it knows it, and then we can do things with it. The fantastic thing about the abstract syntax tree module in Python is that it's built in, right? This isn't some other grammar that every single time a new version of Python comes out, so I have to wait on somebody else to update the third-party AST module grammar so that it matches Python 3.11, 3.12 coming out, because these things tend to change. Because it's a built-in module, I can confidently say that this code that worked here for Python 3.9 will work for Python 3.6, because when I downgrade my version of Python, my AST module will change with it. Now, there might be some new features in the AST module I might not be able to use, a few corner cases here and there, but for the large part, the existing parts won't change. There's a reason that the built-in libraries change so slowly, and that is to not introduce any backwards incompatible changes. But what else can we do with the AST? Well, we can use it to rewrite things. If I have a piece of code that has a bunch of assert statements, maybe these are actual tests that I'm wanting to test, like you see in PyTest, I can actually go ahead and I can execute this code, and we see that I hit an assertion error on line 10. It looks like I see the actual expression printed out. It's this line here. And after, looking at the source code, I can say, okay, well, these two tests passed, this test failed, and I don't think we ever made it to this test. And so what's really interesting about this piece of code is that because we didn't make it to this test, we'll never know if it passes or fails. And so there's a very neat workaround that you can do with leveraging Python's abstract syntax tree, is that you can essentially treat any assert statement as an if. Because isn't assert not just a, if this is true, do nothing, if this is false, raise some error. And you can actually do that with Python's abstract syntax tree. We can leverage this, we can go into the code, and we can use what the AST module refers to as a NodeVisitor. And there's a few ways that you can parse this tree. I'll go ahead and create this visitor class. right? We inherit from it. When we use it in this pattern, we can perform an action. This is very object-oriented. We can perform an action anytime we visit a specific node. And so I want to visit every single assert. And this takes itself as well as the assert that we're visiting. And I just want to visit every single assert, and I'll just print it out. Right, and so we see that I can use this very simple pattern to do something every time I have an assert statement. Now the NodeVisitor is just for maybe I want to log or do something of that nature. I'm not actually changing the tree in any specific way. If I wanted to change the tree and do something more dynamic, I would need a node transformer. And when you lean on the node transformer, you can actually return different things. And so I want to just show you the difference between this NodeVisitor and node transformer. When I actually run this abstract syntax tree, this code, we can see I hit that assertion error. If I swap this out for a node transformer, let me just make sure that's imported. We see that I don't hit that error anymore, which is kind of strange, right? And so what's actually happening here is the node transformer is saying, well, we're changing the abstract syntax tree dynamically. We're taking the source code, we're turning it into this AST, and then we're going to manipulate that tree. And in this case, every time we visit an assert, we're implicitly returning none. So we're saying every time we visit an assert, well, we're actually going to remove this node from the tree, so it's never going to be run because it just doesn't exist in the code anymore. So we print it out, but we return nothing. And this is very interesting because we can return another node. We don't have to return the same assert node. I could go ahead and I could return this assert, and the code will ran as if I'd never used a transform in the first place. But what's very interesting is that I can go ahead and I can write my own logic. I can write my own visit assert and say, instead of returning an assert node, return me an if node. And if this is true, if this test passes, I still want you to print out the test. And if this test fails, here's as it passes, and if it fails, I don't want you to return anything. Or sorry, I still want you to return that it fails, but I want you to continue going. And we get that ability because we replaced the assert node with an if node. The if node will not raise any error, and we can see here that I passed this first test, and I'm even able to extract the contents of the variables at runtime and print them to screen. I can pass this second test, and then you see here that that test that I previously failed, I'm able to give much better reporting on it. This is exactly what PyTest does. If you've ever used PyTest's ability to rewrite asserts, this is exactly how it works. It leverages the abstract syntax tree in order to dynamically change the code that's being run so that you don't have to by hand go through, change every single assert statement that you've written in order to test your code.